All right, today we're going to be solving a dynamics conservation of energy problem. So, at the moment shown, a 48-pound bar is rotating with an angular velocity of 2 radians per second clockwise, right? 2 radians per second clockwise. A spring is attached at the end of the bar and remains vertical at all times, guided by a roller at point C. The spring has a stiffness of K equals 14 pounds per foot and an unstretched length of 3 feet. Determine the angle theta measured clockwise from the horizontal at which the bar has an angular velocity of 0 radians per second. Okay, so let's look at this problem. We have a bar that's swinging downwards at 2 radians per second, anchored at A. We have a spring that's always going to stay vertical, going from C to B, that has an unstretched length of 3 feet. And what we want to find out is at what point does that spring get so stretched by this moving downwards that it slows the bar down to a stop. So somewhere in here, we're going to draw. All right, you know what? Let's go with blue. Okay. Somewhere down here, the bar comes to a stop. And what we want to know is this angle right here, theta. All right. So at this position, we still have the spring attached, right? And that spring has gone all the way up through here to wherever it's going to be up here. Okay, so let's look at where the energy in this problem is. Our starting energy and our ending energy are going to be exactly the same because there's no loss of energy throughout the system from friction or anything else like that. There's only conservation of energy here, so we don't need to worry about any of that. Starting energy of the bar is going to be its rotational energy. Let's go ahead and write that. We have KE rotational energy of the bar plus the potential energy of the bar. So I'll say PE bar plus whatever energy is held inside of the spring. So we have K times X squared over 2. Let's go ahead and make that an X naught. Okay. Is equal to, what's our end system going to look like? Now, will the bar have any rotational energy? No, because it's still. Will it have any potential energy? No, because it's reached its lowest point, right? So what's our only storage of energy? The spring. So all of this energy is going to get converted to the spring. K x1 squared over 2. All right. Now let's go ahead and replace these two initial terms here with their appropriate equations. So the kinetic energy due to rotation is going to be impulse around the moment of inertia about A of the bar times angular velocity squared over 2. The potential energy of the bar is just going to be mgh. Okay, now what is h? Let's start by looking at the mass center of the bar, because that's how we're going to judge our the difference in potential energy off of, is how far downwards the mass center has moved. We'll call this G. Okay. Now, You might say that the distance that it moved was this right here, but actually the distance that G has moved is this distance right here. Well, how can we find that distance? And how can we relate it to X? We want to have as few variables in this equation as possible. In fact, we only want to have one variable in this equation by the time we get done so that we can actually solve for theta, right? So let's relate this height to theta. Well, we know that this distance right here is going to be half of whatever, well, actually, no. If we just take this right here, move it over here, look at that. That distance right there is just going to be half of the length of the bar sine theta. So we'll say that h equals half of L, so L over 2 sine theta. Cool. Of course, in this case, L is 6, so that's 6 over 2, which gives us 3. So 3 sine theta. Okay, so now we've taken h and put it in terms of theta. Let's take x naught and x1 and put them in terms of theta, right? Actually, x naught we don't even really need to put in terms of theta, right? If we go in here, we can find out what x naught is right off the bat. We're told what it is. We're told that x naught equals 1 because the unstretched length of the spring is 3 feet. And what are we at right now? We're at 4 feet. So we've stretched by 1. Okay, great. So x naught equals 1. All right. Now, x at the end is going to equal whatever our initial stretch, which was 1, plus whatever this distance here is. What is that distance going to be? Well, if we take that distance right there and we move it over here, you can see that that again is going to be sine theta times the full length of the bar instead of just half the length of the bar, right? So let's add that to the stretch of the spring. And that's going to be 6 sine theta. All right, now we've put h in terms of theta, and we've put x in terms of theta. Let's substitute everything back in and see where we're at. So I sub a angular velocity squared plus mass, which is 48-pound bar. So 48 over g times h. H is 3 sine theta plus the energy in the spring, which is k, which we know the value of, but I'm not going to put in here yet, times 1 squared over 2 equals k. X1 is 1 plus 6 sine theta, and then all that over 2. Don't forget to square that. Okay. Now, what are our only variables here? I'm going to go in here and highlight. Okay. We know what k is. We know what g is, of course. We don't know what theta is, of course. That's what we're looking for. And do we have any other variables? Well, we don't know the value of this impulse right here. So let's go ahead and find that. So impulse about A of AB. How are we going to find that? Well, the impulse of a bar about one of its ends, the mass moment of inertia of a bar about one of its ends is equal to 1/3 the mass times the length squared, which in our case is 1/3 times 48 over 1/3. 1/3 times 48 over g multiplied by 6 squared. Okay. And what we get from that out of the calculator is 17.905 slugs per, let's see, what's the unit? Slugs per feet squared. Okay. All right. Now that we have that number, we can plug everything into this equation and we'll get our answer out when we solve for theta. I'm going to go ahead and do that. First, let me go ahead and define all of our other variables in here. So the angular velocity to start with was 2. G is 32.17, and K is 14. And I think that's it. Now, once we plug all these in and we solve for theta, we get that theta equals 30.955 degrees. And solving for that, I just used my calculator and put the equations in, solved for the variable. All right. Boxed in. Okay, well, thank you so much for watching. I hope that this was helpful. And if you have any questions or corrections that you'd like to make, then please leave a comment and I'll do my best to get back to you. Have a good one.